Okay, so welcome to the LaMAria tutorial. So I'll give an introduction and then we'll have a number of interesting speakers and I'll get to that at the end of the introduction. You see lots of different partners down here. Essentially, in this case, this is work that mostly has happened at ETH Zurich. And then the key partner is Meta in this, and the Aria should already be kind of a giveaway there. But we have collaborators at Google and Microsoft also in the team here. So essentially the key problem that we're looking at here is being able to for systems where we can add virtual digital pixels, overlay them with the world. To be able to do that in a consistent way, we need to be able to localize our device with a display that allows to overlay this information on the world. We need to be able to localize these devices, like in this particular example, HoloLens or a phone or so, or Aria glasses, or other glasses in the future. You need to know exactly to do an intuitive overlay of information on top of the world, you need to know exactly where the device is located. So you can have kind of pixel-aligned overlays on the world and be able to essentially predetermine what information in the physical world relates to what information in digital world in a kind of one-to-one fashion. Okay, so for that you need to be able to do essentially 6-degree freedom localization in the world. So meaning you need both to find the orientation and the position of the device. And you need to do that actually for every frame. And ideally, you need to do that with 0 latency so that you have it already when you're displaying something. So actually even ideally negative time so that the time it takes to render, you actually can render it at the right place. Okay, so there's challenges there and we talk a little bit about some of the things there, but essentially for simplicity, we need to know where we are, what we're looking at in a quite precise way. To do that, it's important to be able to also do mapping so that you can essentially build up maps that you can then leverage for localization. The kind of doing an a priori map of the whole world, kind of once and for all, or this or that doesn't work. The world is changing, things like that. So typically the systems that we're looking at have these 2 components. If you want to be able to localize, then you typically also need to be able to do mapping kind of first, ideally with the same devices so that, maybe somebody's walking and kind of going for an experience and then that data can be leveraged and, built into a map and then later leveraged for localization of a next person. It also means that you can share information because the first person that walks through that places, essentially annotates the word, let's say, and then the next person that comes, if that mapping data from the first user can be turned into a map that can be leveraged by the second one and localized to by the second user, then you can start building those scenarios where people can start annotating the world and making things like that possible. Again, so there's really this interplay between mapping and localization. So if we do mapping and localization for Aria, we decided against that acronym. So we have localization and mapping with Aria, so LaMAria. So essentially you have that interplay, and then so we create maps so that we can later use them for localization, and essentially in a kind of symmetric way. And this is what SLAM does: visual SLAM, visual localization, mapping, etc. So in the computer vision community in particular, we have kind of these 2 very related problems. One is called structure from motion, the other one is called SLAM, and they're in many ways closely related. SLAM comes typically more from the world of robotics. So the simultaneous localization and mapping, meaning that we haven't pre-mapped and then we localize towards the map, but while we are actually, initially we start a session, we start building a map, and then we also continuously relocalize to the same map. So you do simultaneous localization and then and mapping. Essentially you build a map, and then as you kind of revisit during that session or at some other point you revisit them same spaces, you're actually localizing to the map that you've been building up. And so you do this essentially simultaneously, and essentially you close loops and do things like this. In structure from motion, It's very related. It also tries to solve both the mapping the world structure problem, so that's where the structure is essentially the map, and then the motion is the localization, okay? And so we are solving those two. In computer vision, it's more looked at in a kind of collection of images kind of setting typically. As you see here, you have a bunch of different pictures. In that case, often what's relaxed is it's not necessarily pictures taken at the same point in time. The viewpoints, there's not necessarily the concept of consecutive images, where typically in SLAM, and then in one of its components, visual inertial odometry, the kind of figuring out how you're moving through the scene that you have in robotics, that you have in these kind of sessions on device, where you have a stream of data that's typically absent from the kind of classical structural motion problems. But they're all still very related because while in SLAM and in robotics and so on, you have a session, the next frame, the new frame is very closely related to the previous frame. You have this continuity in the sensor stream that can be used to get really kind of robust kind of tracking going on. If you start building large-scale maps over multiple sessions across multiple devices, then you actually start having a lot more of the typical structural motion challenges that come in, which is I mapped this yesterday, and then I come back here today, and now the lighting is different, a few things might have changed, and so we're much more in the kind of structural motion type of settings where you have to now find, like in this old map, where do I show up in this old map and how do I kind of localize myself? And a few things have changed. Is it still the same place or am I confused and it's a different place, etc. So all the challenges that we've spent a lot of focus on solving in structural motion actually also come back in these kind of continuous streams, kind of multi-device, multi-people tracking and so on. Okay, so why SLAM matters for this on-device intelligence? Well, being able to really place back information accurately in the world is eventually going to make a big difference. If it's to work with a device, you have to press this button. If there's 5 buttons and you can't exactly point to the right button, then this is not very intuitive. If you can only show a picture of the right button and the person has to look carefully and then look at the device and figure out like, okay, I think that's that button, but I'm not completely sure, that's a problem. If you can directly put an arrow on top of the right button, visually that's very intuitive. You don't have to look anywhere else. You stay in the flow. You can immediately press the right button. So that's where essentially having precise maps can really make a real difference. And of course, similarly for robotics and other applications, which can actually all leverage the same type of maps. And so really there's this contextual and spatial AI that allows to, the goal there is to anchor information to space. Be able to, if I want to do this task, then that's the place, that's the, the thing, the tool to pick up, or that's kind of the button to turn, or that's kind of the place to go look for it, etc. So that's really critical there. Okay, so we want to focus on really benchmarking what's possible, what the state of the art is, both what the industrial systems can do, but then also very much we want to help push the academic community to better tackle the challenges that appear in these type of scenarios. What we've noticed as we worked on this benchmark is that the academic state-of-the-art that was trained mostly on, or developed mostly on robotic platforms that have certain types of motions, that have certain kind of rigidity and multi-camera setups and so on, that if you translate that just naively to kind of glass-mounted cameras, these glasses are not perfectly rigid. So calibration and maintaining calibration is important. Your robots or things like that typically don't have like fast head motions. We can turn our head at like hundreds of degrees per second. So we can do this. Like this confuses easily systems that are not, have not been developed with taking these things into account. The problem, by the way, if you quickly turn your head, is not only that it quickly changes, especially with VIO, you actually know that you did a large rotation. But the problem is also that the map that I was nicely building up here suddenly is out of view when I look there. And so you kind of break your connection between two maps. And there's issues like this that show up, right? Also, the kind of environments that we walk through and so on, we don't necessarily realize, but there's actually lots of challenges that happen in practice. So for example, you might walk in a crowd, lots of people, and so all of your nice features that you have in the world might be occluded by other people around you. You can have, as you step from inside to outside or vice versa, you have orders of magnitude difference in the amount of illumination. And that means that typically in the same image, you don't see both inside and outside. And so it very quickly transitions from one side to the other so maybe it can track inside, it can track outside, but it loses tracking while you walk from inside to outside. Those are big challenges because the dynamic range that a normal camera has is actually very limited. And so it can adjust its dynamic range, but it cannot see both inside and outside typically at the same time. I think the Aria 2 there does particularly well as far as I've understood, but still we'll see. So there's challenges in those spaces. Another one is to make all of the modern systems to work robustly and so on, they're all VIO systems. So visual inertial odometry. So they combine essentially visual signals and inertial signals to together estimate the motion. And that works great. Those two signals are highly complementary. So the inertial sensors are really, really good at like the very short-term motion estimation, very robustly and very cheaply, energy-wise and so on. While cameras, except if we're talking of event cameras, and those have their own challenges, but normal cameras, maybe you get a frame every 30 milliseconds or so. So 30 times per second or so. You only get these measurements, and it takes a while because it's a lot of data. It takes a while to process them and so on. And so it's intrinsically a slower sensor. So it's not great at like very fast motion. Also, you get motion blur then typically and so on. However, if I identify a few reference features, landmarks to track, then I can stand it for an hour, and as long as I still see the same features, I will have no drift. I will know that I'm still exactly in the same position watching the same thing. That's something with inertial sensors, they essentially drift. Because in particular, the orientation drifts slowly, the position drifts very fast because you have a double integration. And so double integration of the noise means you very quickly drift off in anything. The two together work very nicely, but there are scenarios where the two don't work so nicely together, which is when the visual world and the inertial sensing don't agree on what they measure actually a different thing. This is what you get if you're in a platform that moves. For example, this is the funicular at ETH, the polyband. And so if you get inside the polyband and you look at the inside, you mostly visually see the inside of the cabin. And then, and so essentially you're visually standing still with respect to the cabin, but you're moving with the device, with the funicular is moving down or moving up. And so the inertial sensor is measuring that motion while visually you see no motion. And so that disagreement means that most visual inertial systems get completely confused there. It's the same in an elevator, it's the same in a car, in a ship, etc. That's something actually many years ago, we had to solve that for HoloLens so that we could actually use HoloLens for helping people repair things on ships, for example, when you're at sea and you can't have the technician, you call in remote help, but nothing worked because the wave action was actually making HoloLens lose track, for example. Right? So we had to address that. There are some ways that you can address that, but again, those are big challenges when you actually use this, let's say, day in, day out, when the ambition is that you can wear those glasses all the time and just use it. Then there are challenges to be addressed there. Okay, and then of course, just holding up at scale and so on, most of the test sequences are actually short sequences, relatively short trajectories or limited and so on. So we really wanted to scale things up. So here's the data set, kind of a preview at the data set that we have. By the way, as we'll see in the discussion, we actually can guarantee a very high accuracy of localization, kind of centimeter scale essentially. If you look carefully here, the visualization here where we used kind of, I think, Google data and so on, like the alignment is actually not perfect here. So that's not a mistake of our accuracy. It's a problem that we don't have the Google models exactly aligned with the world. But anyways, here you see essentially kind of an overlay visualization of all the data that's been collected. And so you see we essentially had in the initial, the previous data set, the LaMAria data set, that we collected both in the main building, in the computer science building, and then in this area on the other side of the river, kind of as separate islands. But then in the LaMAria project, we decided we wanted really long trajectories to be able to keep track and evaluate drift, not by doing a long trajectory, but loop back to the original position, which has some specific kind of constraints on it, but actually to be able to walk in a particular direction for a few, a kilometer or two, and then validate how much error do we accumulate over that. And so here you see many trajectories through the streets of Zurich, collected by Anusha and Shaohui and many students at ETH. And so they'll give you a lot more details on how to use this data set and what you can do with this data set. So we have lots of sequences, a number of different challenges. These are all large-scale egocentric data, and we essentially have of the order of 1 centimeter accuracy by relying on essentially traditional surveying equipment and GNSS, accurate GNSS signals. And so this accuracy is for a number of control points along the trajectories, not strictly at every point of the trajectory itself. So, okay. And so really what we want to do is to stress test for SLAM at human scale and essentially for wearable devices. So where really we argue that wearable devices really have different challenges and constraints than the typical robotics and drone and other kind of and vehicle systems. The motions are much more random and have a lot of different dynamics. And so it's important to also test on those scenarios as they become more and more relevant. So lots of challenges, different challenges, as I mentioned before, unconstrained, moving environments, long distance, and duration that we all made sure to have present in the data. And we have a trustworthy evaluation using surveying techniques at the scale of essentially the whole, the whole downtown Zurich area, essentially. So that was the part, the intro part. So there was this here. And then we'll continue with Jakob, Engel from Meta, presenting large-scale egocentric data and Project Aria in general. We'll continue then with David Caruso, also from Meta, presenting a little bit how SLAM is done within Project Aria, and also how the machine perception services are providing these capabilities to users of the Aria glasses. Then there's a coffee break. Then Shaohui, who's a student at ETH, will introduce the actual LaMAria dataset. And then after that, we'll discuss, and Anusha, Krishnan, who's also starting a PhD in the group, will essentially present then the benchmarking VIO and SLAM baselines using LaMAria and the challenges that we've encountered there, and seeing that those the existing baselines actually have encounter a lot of challenges on the data that we collected, and then essentially a practical guide on how to use that and how to submit and so on, and then we'll wrap up with a conclusion at the end of the afternoon.
I want to give a bit of a motivation why we do all of this. Why do we care about SLAM for egocentric devices in general? I think we are about to see yet another revolution of wearable devices. And I know a lot of people have said that about 5-10 years ago about AR devices. But over the last over the last 2 years really, a lot of devices have come out that aren't for AR displays, but really are about capturing information for you to interact with AI systems that are becoming more and more present in our world. Now, there's nothing new. Every good sci-fi movie has like its version of some device that allows you to interact with AI systems. And fundamentally, these devices act as an information bridge. Between AI systems and digital systems, and you as a human being out in the physical world. And that goes in two directions. First, it goes from AI systems and digital information to you as a human. And historically, that's where actually a lot of the emphasis has been. That's where the emphasis is when you look at like AR devices that have screens, XR devices that again have screens, mobile phones, smartwatches, right? Again, with the screen, they're all there to connect you to digital information so you can see it. I think the next generation of wearable devices is going to be about the other way around. It's about getting information from you as a person and from about the environment that you're in to AI systems so they can help you better with whatever you're trying to do. So really, this is becoming more and more important, and it's driven by two things. First, AI models are now able to process large amounts of diverse, unstructured data in a way that makes sense. That wasn't the case like 10 years ago. And second, we have conversational AI, right? ChatGPT and consorts as a new paradigm for interaction with information in these AI systems. All right. Now, quick show of hands. Who of you has used ChatGPT or Gemini or something else to summarize a paper or find a bit of information you're looking for without actually reading the full thing? That is absolutely everyone. Great. Now, you're going to spend another 4 days here at the conference. You're going to have a bunch of conversations, see a lot of talks, see a lot of posters. You're going to have a lot of great ideas, hear a lot of things that you want to follow up on. And if you're anything like me or jet-lagged, you're probably going to forget following up on about 80% of those. Wouldn't it be great if you had the same kind of ability to use AI systems to interact with, effectively the wealth of information you're exposed to throughout a day, a week, a month, a year, your life, in a similar way, like how we can use ChatGPT today to, frankly, summarize papers for you or find the information you actually need. So that's really what this next generation of wearable device is about. It's about both helping you in the moment, right? There's all these examples of find my keys and help me fix the bike in front of me, or like tell me what I can cook with the ingredients that are standing in front of me. But I think more fundamentally, it's going to be about fueling personal AI assistants that are there to help you with whatever you need help with, and that have access to information to do that. And that's why this other direction, where wearable devices serve not only as a way to get you information and for you to interact with AI, but also for AI to perceive and learn about what you're doing, what the world around you is going to become so much more important. So how much information can a pair of glasses capture as you go about your day? Really quite a lot. So this is a video that combines a bunch of methods that, some of them are public, some of them are about to be public by end of the year, that shows the information that we can acquire from just a single pair of Aria devices. The person in white is wearing a pair of glasses here. Everything you see is reconstructed from that person walking around, including the objects, including their own body motion, including the motion of other people around them, mostly accurately at least. Now, obviously, there's much more than this, right? There's audio, there's eye gaze, what you're looking at. I'm focusing here, obviously, on the spatial aspect because that's where SLAM is getting really important. Now, this is captured with Aria. The sequence I've just shown you is actually captured with Aria Generation 2. I assume most of you have actually been using Aria at some point. This is how the raw information or the raw sensor data from an Aria Gen 1 device looks like. It includes 3 cameras. It includes eye gaze tracking from eye cameras. It includes microphones. It includes accelerometer, gyroscope, 2 IMUs actually, and then a bunch of other sensors. And we're using all of these in combination to effectively get information that then will become useful for AI. Now, earlier this year, we announced Aria Gen 2, and we'll be making that available to the community beginning of next year. Here's a blow-up of how it looks like. It's quite a bit more complex than Aria Gen 1. It includes more cameras, more sensors in general. It has a much, much longer battery runtime. But most importantly, it also features a bunch of on-device processing. So a number of the algorithms that in Aria Gen 1 are available through web services, in Aria Gen 2 are running directly on the device using Qualcomm AR1G1 chipset, as well as our own custom coprocessor. Now, what's running on device includes SLAM, or at least VIO part of it, hand tracking, eye tracking, as well as automatic speech recognition. Really giving you quite a comprehensive suite of components to then build on top of. To learn more, please join us for the hands-on egocentric research tutorial tomorrow, also here at ICCV. Visit the booth or go on projectaria.com. All right. Now, localization mapping, as Marc introduced, is obviously very important. And in fact, everything that I've just shown you is built on top of it. But it's just the beginning. So I want to take the next 5 minutes to do a quick rundown through some of the other algorithms that are built on top of the stack. That is also, that David is going to talk about afterwards, and that we're also using to build the LaMAria dataset. First, object reconstruction, object mapping and reconstruction. So we're about to introduce a new method called Shaper, robust conditional shape generation for casual captures, that is bringing the power of modern generative reconstruction and shape generation methods to egocentric devices. This is awesome work from Yawar, who's also going to talk about it tomorrow in the egocentric tutorial. This is how the result looks like. So what you see here is a reconstruction from a Project Aria device that includes the majority of the object in the room, reconstructed as complete objects. Now, this isn't just this actually does match the real world. This shows a side-by-side comparison of the reconstruction on the left and a matching image on the right of the scene this is obtained from. And as you'd imagine, it is heavily using a generative model to reconstruct objects after they've been detected, but then also using all the additional things we have available from Project Aria. That includes point clouds, it includes SLAM, it includes multi-view images, and so on. I'm not going to go through the architecture in detail. What I do want to point out is that these are all the points that basically are the output of VIO, that are the input to this reconstruction model, and are really key to bringing methods that you've probably seen from image to 3D generation methods to actually work in the wild and on egocentric devices. But it's not just about objects. The second thing, obviously to us humans, probably what's most important is other humans. So here's an example, or here's a video showing what we can do there, showing how we estimate both your own body motion, as well as the motion of people around you that you might be interacting with. So this is a combined video. It shows both the objects and the people. And you can see it's really quite accurate. And using all the cameras on an Aria Gen 2 device, we can really get quite a lot of coverage of what's happening around you. All right. So this is the combination of two core algorithms. One that we published earlier this year at 3DV called HMD2, environment-aware motion generation from an HMD. Again, this is a diffusion-based model that reconstructs motion of the wearer from a couple of inputs, including the VIO trajectory. So again, this is where SLAM and localization comes in. Turns out how your head is moving is really quite informative about when it comes to how the rest of your body is moving. 3D hand poses when they're visible. The point clouds we get from SLAM, as well as RGB images to get a bit more environmental context. And all of this as input then uses a generative model to reconstruct the 3D skeleton shape and motion. And you can see that rendered here in the videos. The second part of this, and this is, we're going to publish this about end of the year, is a method that does all the same things, but for other people around you. What you can see here is a video captured in one of our meta campuses of a person walking around. The person himself is not shown. You can see the little like white frustum that represents where the observer is, and the 4 cameras on an Aria Gen 2 device. And you can see that it's estimating quite reliably the metric 3D body pose and motion of all the people, or at least the majority of the people, around the user. Right. Both of these are trained on the LaMAria dataset. It's a dataset we published earlier last year. It's a huge dataset containing about 300 hours of daily activities in about 50 different locations, mostly Airbnb apartments or houses. It's a lot of video, a lot of head motion, and used to train all of these devices. Now, one of the things to note here is that, again, we're using Aria SLAM system to obtain the ground truth for this data set, both for the head motion, but also for the wrist motion. What I'm showing here is a video recording of an Aria device, effectively, that is attached to the user's wrist while playing badminton. And well, it's a very challenging situation for VIO and tracking system, obviously, like everything that Marc talked about in terms of rapid motion, rapid field of view changes, absolutely applies here. Still, we can track it quite reliably. Give you an example just of the quantity of that data set's data. Here's a video that shows the point cloud of a kitchen in one of the apartments overlaid with all the trajectories from the head, the left hand, and the right hand. Now, an interesting part is you can see certain clusters emerging. One of them being that green and blue cluster on the bottom right. This actually corresponds to a fridge in the kitchen, and you can see that the user is either opening one of the doors with one of the 2 hands, and doing that quite repeatedly. So what you can see here is that humans and objects don't exist in isolation. Obviously, humans interact with objects. Objects inform what humans do. So one of the updates that we are again releasing by end of the year is an update to this data set called LaMAria++ that is adding 3D bounding boxes to all the environments, better human motion, as well as hopefully shape reconstructions for the object in it. Here's a preview of how that looks like. So what you can see here is sequences from the LaMAria dataset, if it was playing. There we go. Right, it's not quite ready yet. We'll fix that by the release. But showing, in addition to the human motion, also bounding boxes of all the objects in the environment, as well as the ground plane that we can use to, for example, avoid things like foot sliding. Right. LaMAria++ is basically the LaMAria dataset, but adding about 20,000 bounding boxes of 3D objects in 47 Airbnb locations and observed across around 300 hours of everyday activities. Right. And with that, I'm gonna hand over to David. Check for updates on projectaria.com/news for some of these things that are about to come out. And yeah, with that, I want to hand over to David, who's going to talk about how all of this is made possible using SLAM on Aria. Thanks.
Hello everyone, so I'm David. I'm a research scientist at Meta, and today I'm going to talk about the Aria location stack, which power the machine perception service we provide for Aria data. So today, if you go on the LaMAria website, on the leaderboard, you see this table. This table contains a few usual suspects in the realm of visual inertial algorithms. So you find OpenVINs, OrbSLAM3, OKVs, and you find something that is called Aria SLAM. Aria SLAM is a SLAM stack that powers internally our machine perception service. And on the LaMAria dataset recorded with Aria SLAM is way better than every open source alternative around. So we'll try to find exactly why this is the case. So on the high level, this service takes the input from the glasses, SLAM, RGB images, and the IMU stream. Takes also as input a factory calibration. Those glasses are calibrated in factory individually and returns 4 things. It returns the open loop trajectory. It's an automated trace that is computed from the data. It returns a closed loop trajectory. This closed loop trajectory is the output of a SLAM system in which we do loop closure handling. And it returns a refined calibration. That means we take the factory calibration, refine it, and give you a better calibration out of the service. There is also an extra output. It's a point cloud. This point cloud is computed using the trajectory from the SLAM service, but it's not by itself the map that we use for SLAM. It's a user of the SLAM service. So I'm going to dig into how we actually compute this trajectory and calibration. We have 3 stages. The first stage is visual inertial odometry. So from the data we get from the glasses, we have a state estimator that maintain an estimation of the state and the uncertainty, pose, velocity, and calibration of the device. And each time we have a new IMU measurement, we actually update the state by integrating the IMU. That way, we can predict where will be the next images from the IMU and use this information to aid a sparse optical flow algorithm to detect features and corner from frame to frame. So here in that algorithm, cameras and images are actually summarized into a set of very short-term tracks that are tracked from image to image. This algorithm doesn't have a lot of memory. It keeps like 10 keyframes, so it's roughly like a few minutes of data eventually. But it's super cheap, it's fast, it runs synchronously with the IMU and the camera. For each images, we have a new pose, and it's causal. We don't really estimate past pose. We only estimate the current pose of the current images. So in literature, the thing that are the most similar to this algorithm is a line of research about MSCKF from Tassos Morikis. So this algorithm gives us an odometric trace, that's the open loop trajectory that we returned. In order to get a trajectory a bit more accurate, what we do is we feed this odometric trace to a visual mapper. The best way to think about this visual mapper, it's an odometry-aided visual SLAM system. It only works on grayscale camera, and it represents the world as a set of landmark points in the world that are described with appearance descriptor. You can think of appearance descriptor as, like, for instance, an orb descriptor that is found in the literature. Then, from all those descriptor and corner we see in the image, we create a map using structure for motion method. And there is a bit of ending about multi-map because we want this map to actually scale to campus-wide or building scale spaces. And also we want this algorithm to be quite efficient, that it can run asynchronously but in real time on device. So there is a bit of handling there, but essentially that's very similar to algorithm in literature like OrbSLAM 2. So the output of this is a closed loop trajectory that has loop closed, but is potentially jumpy. The trajectory is a bit jittery. So in order to refine that, we have a last step that this time doesn't run at all in real time. It's a vision inertial bundle adjustment, and it takes the input of as input the output of the previous state, and will optimize the full trajectory, the full calibration parameter, modeling the full knowledge we have about the physics of the sensor in a batch way. So it's super slow. It's done offline. We can afford to do it because the service is totally offline. People send us the data encrypted. We process them and send back the result. But that's what gives us the best outcome. So if you've been in SLAM field for the last 20 years, there is nothing really surprising about this pipeline. There is nothing really new in terms of high-level flow. But then, why does this pipeline actually works way better on the LaMAria dataset compared to open source data? So that's what I want to dig a bit more today. So this plot is just a graphical representation of the table you have in the LaMAria dataset that compare methods that use at least two camera and one IMU. Here it's OpenVINS, OKVIS, and Aria SLAM. And that's the bar chart is the score we obtained by the scoring system of the dataset. Now I want to add another data point on this plot. And the data point I want to add is the score of the visual inertial odometry system before loop closure and before visual inertial and banal adjustment. So we see that this new data, the Aria 0, is worse than the full SLAM system. However, it's not that much worse, especially considering the score of the open source alternative here. So the reason why it's not that much worse is because the LaMAria dataset has a lot of trajectory going from point A to point B, where there is no real loop closure to correct the drift from the VIO. If we look at other datasets, and there is a very good dataset that was released before LaMAria, it is called the Hilti dataset. This Hilti dataset has a lot of good sensors, like the sensors used are actually very good for SLAM. And if we run Aria MPS and VIO on that, we do see that Aria MPS score like twice the number of points than VIO. Here the loop closure are very useful. But even on that challenges, VIO is way better compared to all the competitors in 2022 that participated to this challenge. All the competitors doing also SLAM and loop closure there. Actually, Aria MPS is very competitive compared to LiDAR method on this dataset. But clearly, it's not only the backend. It's not the SLAM system we are doing, the loop closure we are solving for, and it's not the visual inertial banal adjustment that makes this thing work so well. So what makes this thing work well is actually the odometry part. The odometry part is an algorithm that does sensor fusion between the 3 cameras on the glasses, but also the 2 IMUs. But in order to fuse properly the sensor, you need to know a lot of things about your system. You need to know the camera projection function. You need to know how the camera are positioned with respect to another. You need to know how to time align all these data coming from different sensors. And you need to know the error model of IMU. So the more sensor you get, that's nice because you have more measurement. But if you're looking for very accurate fusion, that also you add more chance to have unmodeled effect in your probabilistic framework that power actually the state estimation. And those things are tricky, especially on glasses, because, for instance, the position of the camera one to another can change. If you take the glasses and slightly bend them, you will actually move the display, one position of the camera with respect to the other. So here it's a video of foundation stereo. Foundation stereo is a state-of-the-art way of generating depth map. It's a machine learning model from NVIDIA. And here we apply foundation stereo on the data from Aria Gen 2. And while we actually run the depth map generation, we slightly bend them up, the glasses. And you can see the depth spline here for the whiteboard is actually shifting nearly like 30% away. Because those models, even if they are machine learning based, are actually using the fact that we know the position of the camera and the projection function because we feed rectified images. So actually for modern VIO is really a misnomer. What those algorithms are doing is not only regressing odometry. They are actually estimating the full device state. They're estimating the bias of your sensors. They're estimating the position of your camera with respect to other camera and other sensor, the projection function, and the time offset between everything. So the O for odometry stands for what is the target, but actually when you develop those kind of methods, what you should focus on is how good the state estimation of the device is. And once you shift to this mindset, you can actually use a lot of constraints. For instance, the deformation. The position between camera, your device cannot deform randomly. It has like some mechanical property you could try to model directly in your state estimator. If you use a MEMS from a constructor or manufacturer, the manufacturer will potentially do some like pre-processing of this data for temperature compensation. If you don't know what it's doing, you might not be able to model correctly, but if you know what this manufacturer is doing, you can actually take that into account in your model. But by far, the worst offender to accuracy is any error that actually arises from time modeling in your system. So maybe we can take a step back here. What is the timestamp of a corner observation? So VIO track corners on images, but for instance, these images has been exposed for 14 milliseconds. So 14 milliseconds doesn't sound like a lot, but as Marc mentioned before, like egocentric data, the head rotation can be 100 degrees per second. Let's say 300 degrees per second as a very, very conservative estimate. Then during the 14 millisecond this image was exposed, you have 4 degrees of rotation. 4 degrees of rotation. If you convert that to pixel for this, for the SLAM camera we have on Aria, it's 16 pixels. If you convert that to pixel on the RGB image, because of the high resolution, is 100 pixels. So when you detect a corner on the thing, you actually detect a corner on an image, you cannot really associate to a timestamp up to the 14 milliseconds. So when you want to use this data to fuse with the IMU time series, you need to associate a timestamp. Which one do you choose over the 14 milliseconds? So one way to answer this question is to trying to estimate the timestamp correction in your problem. So you solve the reprojection loss, you solve it, you minimize it, and you estimate what is the timestamp correction you want to use to minimize this thing. And not surprisingly, you find that it's better to use the center of exposure of the pixels that I've seen the center. It's not surprising, but what is maybe surprising is like if you try to associate the covariance to the estimation, you get uncertainty of some millisecond accuracy, meaning that minimizing the projection loss over the timestamp correction gives you something that is accurate up to some millisecond accuracy. But some millisecond is actually way, way smaller than the 40 milliseconds of the exposure. And for instance, if you have a camera, like the camera from the 2 RGPD dataset a lot of people are still using for evaluating SLAM, this camera has a running shutter. What it means is the first row and the last row are not exposed at the same time. They are actually 20 milliseconds apart. Now, those 20 milliseconds means 6 degrees, and those 6 degrees means 60 pixels. That means that if you don't compensate for that for egocentric data, you actually have errors that arise from this time modeling error that are way, way bigger than the calibration error you actually solve for. When you calibrate a camera, you expect to have 1 pixel of error, not 16. And even on devices that are engineered for SLAM, actually, we have some effect that you need to compensate data at the level of the millisecond. For instance, for frame set composition, Aria has 3 cameras, 2 SLAM and 1 RGB, and we try to trigger them at the same time. But in practice, the center of exposure of each camera is not exactly at the same time. It could be 1 or 2 milliseconds off. We don't lie on that. Like when we record data with Aria, we give you the raw timestamp, we give you the correct timestamp. But if you don't compensate for this 1 or 2 milliseconds, on the SLAM images, you have 2.4 pixels of images, or pixel of errors. The RGB image is also a running shutter camera. And here the readout time can be between 5 and 16 milliseconds, depending on your correction, which translates to 60 pixels. That's why when we return the online calibration from the Aria from MPS, we have a per frame calibration for the camera. We do return the fisheye, we do return the projection parameters, and we have an open source implementation of our custom projection function, but we also return time offset that you should be able to use to actually get a better projection. We return the time offset as a timestamp error. That means if you take the timestamp of the raw images, you have to add this value to get the real timestamp of the image. And we do return the readout time, so you can compensate for the running shutter effect. And so with this calibration, here what is the standard projection model of Aria, if you want to use the best calibration we get from MPS. Let's say your problem is like you have a corner observation and you want to unproject this 2D coordinate in the world frame. So the first thing you do is you read the image, you detect the corner. And from the image you read from the raw data, you get a timestamp. You query the online calibration with that timestamp, and you get a timestamp correction in the online calibration. So you apply it. Then, if you are processing the RGB, you apply the running shutter compensation for that pixel, meaning like if you detected your pixel somewhere in the images, you will correct the timestamp differently than if it's another row. Once you have that, you have a correct timestamp to actually query the trajectory from the Aria MPS output to get the pose of the camera. Once you have the pose of the camera, you can unproject using the own projection parameter. And this is a function that links a coordinate to a 3D array in the world frame. It's not a trivial function. It depends on a lot of calibration parameters. But if you do that correctly or incorrectly, that matters a lot. For instance, one of my coworkers published a paper about photoreal scene reconstruction. So think about NERF and Gaussian splat reconstruction. And in that paper, they did an experiment where they had a fixed point cloud in front of the RGB images, and they used a the calibration, and they use the calibration compensating for time offset or not. So here, the red line are actually the difference between the output of the two calibration applied. And if you measure the length of those red lines, on this data, you can get up to 20 pixels or 40 pixels. So it's not totally theoretical. Those things actually matters in terms of like real application. And if you do your reconstruction using one or the other of the calibration, you will find that actually if you do the thing correctly, you get sharper images. Here it's on the right panel. You see, for instance, on the bike rack, that picture a lot of high frequency in the image. Everything seems to be sharper, more contrast, less blurry, than if you use actually only the factory calibration and not compensating for time offset. So for those kind of things that need pixel accuracy, accurate projection and non-projection function, you really, really need to actually compensate for those things. And this is something on the camera, but your system is filled with a lot of small things that you can model better compared to what is done usually in papers and in the open source code. One of the example I like is from the Hilti dataset. So Hilti dataset is a very good dataset, very good hardware, very good ground truth centimeter level that is a bit smaller in scale than LaMAria, but in essence quite good. The way they get position ground truth, however, is by taking the device and putting it on the surface on which they have a marker that they previously localized at centimeter accuracy. But when they do that, that induces a shock on the IMU. And for a few hundred milliseconds after this shock, the IMU depicts some kind of oscillation that I don't think they are physical. I think they are more due to aliasing or maybe like a mechanical damping on the IMU. The thing is, if you try to use the IMU equation on that, it just doesn't work. The prediction doesn't work. So if you don't take that into account on the Hilti dataset and model that explicitly somehow, the score we have, even with Aria and PS, is on par with actually the competitors on the challenge. So there are a lot of small things like that you have to get it right to make odometry work very well. But if you do, actually you get some surprising results and something that are truly impressive. So this time, this is the sequence from the LaMAria dataset in which the user of the Aria go into the polyband Marc was talking about. It's a train in Zurich. So right now we are still on an inertial frame. We are not in the train. But what you will see when the glass starts in the train and the train actually start moving, we still track the position of the glass with respect to the world, not with the train, but with the world. So yeah, we enter the train now. And at some point the train is going to start now. And what you see when the train is starting is that we don't track any features in the train anymore. We track every feature outside of the train. Because by bundling the sensor currently, we actually always have a good estimate of the state of the device, and we know the device is actually moving, looking at the IMU in the world frame. And just by doing statistical outlier rejection, we are able to reject everything that is not conform to this hypothesis, to our current state, and that means everything inside the vehicle. There is no segmentation mask. We don't detect window explicitly to actually try to track the outside world. That stems only by the fact that we have a good state estimate at all time. And on this sequence, after going down the hill, I think the user will go back to the first station, and the final drift is something around 3 meters. So admittedly, it's a cherry-pick data. Not every LaMAria data with a vehicle can be processed that way. But it gives you the power of actually modeling every physical property of your system. Now, sometimes you want to track with respect to the vehicle, for instance, on VR and MR. And that's what also Marc talked about HoloLens. Then usually what you do is you try to add into your state some knowledge about what is the motion of the vehicle, so you can estimate both the motion of the vehicle and the motion of you in the vehicle. But then, if we combine with the previous slide, maybe you can do both at the same time. Maybe from one glasses, we can track our motion with respect to the vehicle and the motion of the vehicle with respect to the world. And that's an experiment I've done with a prototype of Aria Gen 2 here. Aria Gen 2 gives you HDR image, so that solves every overexposition you usually in that case. But what I show here is like on this image, I actually project a map of the world in the SLAM images, and I project a map of the car in the SLAM images too, and you will see that they match with the real images, meaning you can actually accurately track from only the glasses sensor both reference frame at the same time. And again, there is no explicit segmentation of which point or which part of the image belong to which. It's only done at a statistical level inside the estimator itself. Again, it's a cherry-pick data. It's not something that is solved in general, but it gives you, again, an example of what you can do if you model things correctly. Now there is even a bit more fun example of non-inertial frame and vehicle. So this one is a trajectory that also computed with VIO. Where's my mouse? On a very long trajectory. This trajectory spans over 4 hours in a building. And again, the trajectory that we display the odometry trace, there is no loop closure done here. It's really the raw performance of the odometry system. What is interesting with that trajectory is it's a trajectory over 4 hours. And over 4 hours, the Earth is going to be rotating. The rotation rate of the Earth is roughly 15 degrees an hour. So here, that means while you were recording this trajectory, the Earth rotated 60 degrees. That means if you have a perfect gyro and you integrate it without taking into account the Earth is rotating, you will do an error of 48 degrees. You have to compensate for some latitude effect. Let's say around 50. But if you look at the odometry trace, it's easy to see roughly from the odometry trace the error you did on the angular part of the motion. Like this long corridor here, you can see that every time we walk this corridor, you can see that we actually slightly drift in angular. But if you look at the rate of the drift, you can see that over 4 hours we drifted something around 6 degrees. So we drifted less than the error that would have been caused by the Earth rotation, even if we don't really model the Earth rotation here. I'm not claiming that you can actually find the north by gyro compassing here. What I'm claiming is once you have those good model of your hardware, you also need to refine the hardware of the environment. And it's not non-reasonable to think that now this kind of system needs to take into account the fact that Earth is not an inertial frame. So that's kind of interesting, but what can we do with an odometry that is as good as this VIO? That actually opened quite a lot of research direction. So Jakob talked about the LaMAria dataset. The fact that we add the temporal modeling done right is the reason why we can actually track the motion of wrist. Wrist is going to be way, way higher in terms of dynamic than 300 degrees a second. So if you have any time stamping error here, you will lose track quite easily. Another dataset for which we were really helped by having a very robust VIO and SLAM stack is the EGO-EXO dataset. So this dataset, the goal was to record activities from human for a few minutes. Here it's a sequence where we record someone dancing. But the way this dataset was recorded was a bit complicated because you have several cameras everywhere. You want to have external point of view and internal point of view of this activity. And so you have to calibrate a lot of GoPros all around the scene and calibrate them in the same world as the Aria glasses. So the way we recorded that is by turning on Aria for the 2-hour session before we started to do any calibration. And we basically process the 2-hour sequence as one block. And we were able to track the position of the glasses, even while the glasses was actually not being taken care of. Sometimes it was because the performer was actually adjusting the glasses on his nose, or they were switching glasses with another performer, this kind of thing. And VIO just tracked everything. And for this dataset, it was super helpful to be able to record 1,000 hours of data to have a system that actually just works. But even if you are interested in location problem, having this kind of trace, very good trace of photometry and block using some new kind of information. There is something a lot of people talk about, but nobody really made it work, is magnetic mapping in buildings. The magnetic field in buildings cannot really be used for measuring north. But if you map magnetic field magnitude on the trajectory I showed you of 4 hours in the same building just before, you can clearly see that there are areas of the building that have a very specific magnetic field magnitude. Now, usually this is very hard to read because magnetometers are like, they are noisy. It's hard to model. There are magnetic perturbators that might actually be non-static. But if you have a good odometry, now you end up with a problem where you have an array of magnetic measurement that is actually easier to handle. Usually, if we start to look at that, what you want to do is crowdsource your data. You want to have an always-on system, SLAM system that runs on the device from people that you can, in the background, actually map the world. Problem is, if you want to do that in cities, you cannot, if you want to do that, usually you need a reference frame where you express the map of the world. And you choose the Earth's GPS reference frame usually. But in cities, or urban canyon, GPS is not going to give you anything really correct to geo-reference your data in this reference frame. But if you have a good odometry running always on, what you could have is get a GPS fix in a park when you have open sky and a lot of satellites that can be 10 centimeter accurate. That's the kind of thing you can actually expect as accuracy for modern GPS sensor, even on phone. And you can propagate this to a building in which you don't have any GPS information, but since you had like 1 kilometer away, you had a good fix, you can actually know where you are on Earth by integrating your odometry. And you can apply this reasoning to visual map too. Here, before I was talking about very sparse GPS fix, but one of the problems we have with a SLAM map in general is like they are quite heavy. It's a big point cloud. Each point in the point cloud are actually described as a descriptor. It takes a lot of memory to store. But if you have a very good odometry like the VIO we have, maybe one way to solve the problem is to have less points, but of better accuracy. So you end up maybe in a realm where you might want to only map like semantic point, the point of like corner of door or corner of wall. And if you do that, you actually simplify a lot of your problem because your map fits better in memory. So you could store on your Aria glasses map for the last 2 weeks you ever visited or this kind of thing. And at Meta, we believe in that vision where if you have an odometry that just works, there are a lot of things that you can unblock. Aria Gen 1 had the machine perception service to compute VIO, but as Jakob mentioned, Aria Gen 2 can compute VIO directly on the glasses for hours on a single battery charge. And the algorithm that compute VIO on this Aria Gen 2 is actually on par in terms of performance with what I showed you today. So having odometry just being a modality and a sensor on glasses is something that we have to prototype of those kind of things today. And so you can start designing SLAM systems that take that as an input and don't necessarily have to recompute it. And there is a parallel here to do is when 10 years ago, people actually start using the Kinect. The Kinect was also providing some kind of indirect data, like it was computed on the data of the camera. But the reason the Kinect was used is because it was giving some information it was super hard to get in another way, because it was integrated into a chip there. And so there might be a chance that in the future, odometry is just a modality you fit either to your SLAM stack or either to your machine learning model. If we want to get there, and if we want to start working on the challenge I mentioned about crowdsourcing data using weak signal, what do we need to move forward? I think what we were lacking is actually good data set with large scale, capture with a good device that has a very good ground truth so you can evaluate your performance on a realistic egocentric scenario. So that's exactly what Aria and LaMAria actually provide to the research community, and I'm very excited to see what is going to arise from that. There are a lot of research directions that could not be evaluated correctly before, and I think now it's actually solve a lot of those problems. So thanks for your attention, and if you have any question, I can try to answer them.
Welcome back. So thanks for coming to the tutorial. And I'm Shaohui, a PhD student from ETH Zurich. I'm from the group of CVG, advised by Professor Marc Pollefeys. And I'm gonna talk about a full introduction to this LaMAria dataset in the next hour. So for who weren't in the last hour, I will first give a brief motivation following 3 amazing talks from Marc, Jakob, and David. So we aim to solve the problem of visual localization, and it refers to finding out where we are, and essentially for visual image, it corresponds to solving where the picture is taken. So this is a common problem faced by all of us when we need to navigate in the city. On the other hand, mobile devices like phones and glasses need to also know where they are, because once they know where they are, they can enable a lot of 3D augmented reality applications. And generally, when we talk about visual localization, we talk about the location and orientation, generally with respect to a given coordinate frame. And in the case of LaMAria, it would be like Swiss coordinate system in the Earth coordinate. And each frame is often represented as a 6-dimensional pose that includes a 3D position and an orientation. And of course, when we talk about localization, we also need to mention mapping. So visual mapping refers to building such maps from images, and this process requires knowing precisely where the images were taken. So essentially, mapping and localization are a highly interdependent problem, and they benefit each other, and they are coupled a lot. That's also the reason why SLAM is termed simultaneous localization mapping. And as Marc has already talked about, there are a lot of algorithms in the academic community developed for structural motion and SLAM. And they essentially kind of solve a similar problem with different flavors. So SFM generally works on unordered image collections, while SLAM generally works on video streams that often requires works on device, has some latency requirements, and is sometimes also helped with multi-sensor setup. So essentially, both of them turn images into camera poses and a 3D model of the environment. And for SFM, most methods rely on image matching and geometric optimization, and in SLAM, they are more tracking, and but in the end, they all rely on backend optimization and also as state estimation and optimization. So if we talk about single image visual localization, in nominal cases, it's pretty much solved with quite high accuracy and robustness with respect to a 3D model. So people just generally do image matching and propagate the 2D image matches to 2D, 3D correspondences, and do some PMP plus ransack, and you can get very accurate 60 pose if your calibration is very accurate. However, there are many challenging scenarios remain, which include large appearance, structural, or viewpoint changes between the mapping and the core images, and also the existence of motion blur or occlusion can make this extra challenging. So all these challenges are what we as people who build a data set would focus on. And as I'm going to talk about, this was also covered in the 2 iterations of dataset. The first iteration of dataset is LaMAria 3 years ago, and also in the current SLAM dataset, we also aim to cover all these diverse challenges. So on top of the visual localization benchmark, SLAM has its unique challenges, and also especially for egocentric data and contextual AI, there are also a lot of unique SLAM challenges that do not exist in single image localization. So first, the system needs to localize regardless of user actions. So in the real world scenario of contextual AI, the user's motion is generally unpredictable, so they can move fast, they can look anywhere or even block the camera. And the SLAM system has to stay stable through all of that. So this set of unconstrained views, motion, and things can make the SLAM data particularly challenging. And second of all, we are dealing with heterogeneous devices. So there are different cameras, different sensors, and we also want to build a SLAM system that can generalize across different sensors through it in different devices. And this can be particularly challenging because different devices can have different deformation patterns. So all of these are of the interest of SLAM research development. And finally, we also have a very high accuracy requirement. For contextual AI, it's not enough to just map the world, but also when we add some visual effects, virtual objects must align perfectly with the real thing. So we need pixel level alignment such that digital content feels naturally anchored and stable. So overall, SLAM in contextual AI means robust localization under any motion across any device, and with a fine enough precision to seamlessly blend the real and the virtual world together, such that we can do a lot of subsequent applications on top of it. There are a lot of existing data sets, but they do not really capture all the general conditions for augmented reality and real world wearable devices. So there are many data sets focused on driving scenarios, but this car motion is generally having different motion patterns because cars generally only move, have a forward motion, and the motion pattern is quite simple. And there are also SFM data set that only has single images, which are useful for developing geometric algorithms, but not relevant to SLAM development. Many data sets only focus on single or limited scale environments, and they do not generalize to large scale data. And also, in particular, a lot of data sets rely on some algorithm to build the ground truth for sharp motion and SLAM, and many data sets rely on LiDAR SLAM or other algorithms to construct the ground truth. But when you rely on such algorithm, the ground truth is always not really unbiased because it can benefit algorithms developed in the same flavors. And finally, data sets generally do not have a good sense of temporal changes, and all these limitations of the existing data sets make building a data set for localization and SLAM highly important. So here are the current practice of the SLAM evaluation. So on the left, we show a classic SLAM data set called Zurich MAV. Basically, all the SLAM papers need to evaluate on top of it. And on the right is the TUM Visual-Intertial data set. These are the two most widely used SLAM datasets in research papers. However, they all have very limited scale, and they all rely on platform-based setup. So on the left, there you can see that the Zurich is recorded with a drone with a multi-camera setup, and the TUM dataset is also highly dependent on robots and handheld devices to be able to record. But if we check all the relevant academic publications, so here actually we list the 3 top academic open source SLAM pipelines from the evaluation of LaMAria dataset. And here you can see that in all the 3 papers of OpenWinds, OrbSLAM 3, and AlgoWiz 2, they only evaluate on Zurich and the TUM-VI dataset. And this actually shows a high risk of the current status of the development of SLAM community, because all these datasets are a small scale and they do not reflect the challenges of egocentric data, but also they cannot reflect the limitations on the fine-grained drift, which comes to, for example, centimeter level in a kilometer level trajectory. And so both of the Zurich dataset and the TUM dataset have only short recordings, and also they exhibit high level of saturation. So most of the system already kind of solved the dataset very well, and they are just comparing between 0.3 to 0.2. And this also motivates us to build such a dataset that is large scale and reflect the real egocentric data challenges. Of course, there are also other interesting SLAM datasets available there. Nominally, there are 4 seasons datasets recorded across 350 kilometers, which is an ultra large scale dataset from TU Munich. But all data are recorded with sensors mounted on the car. And as I mentioned, when you record with the car, the motion pattern is quite simple because you generally only have the forward motion in the majority of the data. While in egocentric data, you have a large variance of the heights of the head motion, and also the motion is quite complicated compared to the car motion, which is quite stable. And secondly, there is the New College dataset, which includes a lot of handheld videos. The ground truths come from the LiDAR SLAM, but the handheld videos also does not really reflect the challenges of egocentric data, while being comparably closer to than the car is still far from a good representation of the egocentric data. And in the third column, there is this nice data set called Heat Islam. They also have a leaderboard available. Also, David has done some experiments on top of it. And it was recorded with a handheld and robots. While they also use surveying instruments to build a good accuracy of ground truths, they do not have a complicated head motion. And in contrary, our dataset depends on Aria devices, so we can have a better representation of the egocentric motion. And finally, recently there is this VBR dataset called Vision Benchmark in Rome, which is quite relevant and very good in terms of dataset construction. It also has multiple sensor setup and a very good level of ground truth. However, because they set up the whole sensor suite themselves, they were not able to scale the dataset very well. And I think that's also understandable because they also need to build the whole sensor suite and mount it through on the car or through the handheld recordings. So in the end, they only have 6 sequences available, while our dataset benefit from development of Project Aria, which naturally makes our recording capture highly scalable and do not get blocked by the bulky devices from such construction of the sensor suites. And with all these data sets discussed, we come to a conclusion that we are highly missing the egocentric data. So here, what we mean by egocentric data is that we want height-mounted camera motion, heterogeneous sensors, and also with the always-on nature, we'll have some time-varying calibration on the data as, for example, the bending or the vibration of the devices all can contribute to drift accumulated through a long duration of time. And aside from egocentric data, we also want to jump out of the limited scale data sets and consider longer and continuous recordings to benchmark against always-on contextual AI. And finally, we want some accurate and unbiased ground truth annotations that is agnostic to different flavors of SLAM algorithms. In our case, we benefit from control points from the survey grid instruments. And these kind of unbiased ground truths enable us to benchmark on highly challenging scenario, for example, moving platform, where on some of the sequences, even the best performing Aria SLAM also struggles, but we can rely on the GNSS RTK measurements to evaluate those recordings. So we also collected controlled experimental sets where the motion gradually come from the platform-based motion to the egocentric motion. And the controlled platform-based motion is basically similar to the motion exhibited in Zurich IMUs dataset and the TOM Visual-Intertial dataset. Well, the egocentric motion is true freeform head-mounted motion, where it is more complicated, has a lot of out-of-plane and in-plane rotations. And we figure out that actually most monocular open source SLAM only works on easy data. Here is the controlled platform-based motion. And in the next hour, Anusha will talk more details about the results, but this also motivates the need of the egocentric data, as in the sense that the current existing data set cannot reflect the limitation of the open source SLAM system, as they are very saturated and they are not challenging enough. And on the other hand, when we record with egocentric devices on long recordings, we have a lot of calibration challenges where both camera calibration and IMU calibration are highly time dependent. So with the radial distortion, the focal length, and also the time varying bias in the IMU modeling, they all are not really constant with the factor calibration. Instead, they have time varying random walk that is needed to be modeled, and also because of the vibration and the bending of the devices, the sensor configurations are also not constant to the factory calibration. And all these can contribute to the challenges of long egocentric recordings for SLAM systems to work well to achieve highly accurate results. And all these subtle details, as in the discussed in the last hour, actually contribute to non-negligible drifts in long sessions. And in the top right, we also show a sample example of the focal length and rig extrinsics from the MPS output, where they exhibit larger than 0.5% difference from the factory calibration. And from unconstrained navigation of the egocentric recordings, there are also a lot of unique challenges. And nominally, first of all, there are a lot of long outdoor trajectories, which poses all these challenges of the data. And secondly, when people go from indoor and outdoor, the indoor-outdoor transition often poses large exposure changes, which can make tracking very difficult. And on top of it, there's also low light scenarios where the noise becomes significant and the detection and tracking becomes more challenging compared to the normal circumstances. And finally, we also include moving platforms, where in such cases, there is a high inconsistency between the visual signal and the inertial signals. And this requires some specialized modeling to get the system to work. So motivated by all these challenges back in 3 years ago in ICCV 2022, also from our lab, our colleague Paul-Edouard and Mihai collected this LaMAria dataset, consists of 3 main places: an office building, a university building, and an old city center. Where in this dataset, they gather hours of data over more than a year from users navigating these spaces with AR devices. In that case, it was hand-mounted HoloLens devices and handheld Apple iPhones. These devices are equipped with multiple sensors, such as cameras, IMUs, and radio receivers for Bluetooth and Wi-Fi. So the trajectories were accurately registered into a common reference frame, where we got a 3D model from laser scanners acquired also from Navis laser scanners. This enables benchmarking of single image or sequence visual localization with respect to the 3D scans. The dataset actually reached many researchers and has already accumulated more than 100 citations in the community of visual localization and post-graph optimization. However, they only focused on 3 buildings, and in this follow-up extension, we aim to extend it to a city scale which spans the whole city center of Zurich. However, let's first get back to the dataset building process. So this was a while ago, and if we look back on the efforts that went into the construction of LaMAria dataset, initially we thought creating a dataset would be very easy, but actually we need to first collect the devices, and also we need to write some custom recording tools because the Apple iPhones were not made for research purpose. And after record some data, we also need to anonymize the faces and license plates, and all these back in 3 years ago need to be resorted to some third-party companies, and we also need to pay some money. And in the end, we also need to compute the ground truth poses. Actually, when the LaMAria dataset was initially constructed, the ground truth was built with superpoint superglue. And as you may know, both of them are with a not permissive license. So the release of the ground truth poses also took quite a while. And all these challenges made the dataset building process very, very difficult and tedious. But with the current good progress of Project Aria, everything becomes significantly easier because we don't need to write recording tools, and we also have the Aria supported Eagle Blur to anonymize the data, and all the relevant sensor sources are well exposed from the Aria research kit, which is very good. And although it still took us a whole year to record the whole data, but it was shorter than LaMAria, which took like 1.5 or 2 years. So it's a good improvement. So on the left shows a recording tool written for the LaMAria data capture, where we really needed to write app to make the recording scalable and working. But now with the Aria research kit and the Project Aria classes, we can just go and record and just put the data down, and we just get all the sensors out of it, which is very nice. And secondly, this we definitely need to blur the faces and license plates because these are very important aspects of the dataset. But actually, open source options for data anonymization are not very accurate, and they are highly sensitive to challenges like motion blur and low resolution images. While commercial options are quite expensive, actually back in the LaMAria datasets, they in the end resorted to commercial options. But now we have the Ego blur, which is well exposed by Project Aria, and it is easy to use, open source, and it was designed exactly for the Aria recordings. So we don't need to do a lot of things. We just record and pass the data to Ego blur, and with manual checking, generally it works quite nice, and it can help us blur a majority of faces and license plates we aim to blur. And last but not least, there is also Aria exposes all the sensor APIs and hides nothing from the users. So it's perfectly suited for dataset constructions. And on top of it, also provides a very strong offline SLAM, which is supported by our evaluation. Is far better than all the academic solutions, and is freely accessible via the Aria machine perception service. So all these benefits make our new dataset capture quite straightforward, and so bring a lot of new opportunities to scale up the dataset with egocentric devices. And we also don't need to rely on the laser scans of the environments, which was needed in the LaMAria dataset. So last year, with all this motivation, we decided to kick off this new dataset construction, combining the LaMAria efforts with the Project Aria devices. And thanks to the scalability of the devices, we aim on large-scale SLAM rather than single image localization in this time. And over the LaMAria dataset, we create a dataset that it is large-scale, spanning a whole city center, and exhibits real egocentric motion patterns. And we also have much more accurate ground truth annotations from serving instruments. So here is the dataset. As you can see, we collected a total of 83 sequences in the city center of Zurich, all with, I think only two of them are handheld, and most of them are with wearable devices, in our case, Project Aria devices. And our ground truths come from the survey grid control points, which is centimeter accurate in the XY longitude and latitude space. And we also include a lot of unique challenges, including low light conditions, exposure changes, and also working in the moving platforms. And all these challenges are also explicitly grouped such that we can benchmark different SLAM behaviors on different challenges for evaluating visual inertial odometry and SLAM. And so in particular, we identify challenges of the egocentric data. So first, we group the data to short, medium, and long, and such that we can specifically benchmark SLAM behaviors on the long sequences. And secondly, we include moving platforms, which involves traveling in a tram and also traveling in a funicular in Zurich. And our data also has sharp exposure changes, comes from indoor-outdoor transitions. And also we record some recordings in the evenings to enable running SLAM on low light conditions. And the challenges are not only present in data, but also explicitly defined into groups for easier research purpose. So as an overview of the dataset, we have 22 hours of egocentric recordings spanning 70 kilometers. And we explicitly group all the recordings by 5 different challenges, namely short, medium, long, low light, and moving platforms. We also have a controlled experimental set which includes 13 sequences and 4 different levels based on motion patterns. This was the one from the platform-based simple motion to the egocentric motion, and this was for better prototyping of the open source SLAM to help them close this gap to make sure that people hopefully don't get discouraged from such a large gap between from your MAV dataset to our dataset. And in our main dataset, we have 63 sequences with hidden ground truths where people can submit via the online leaderboard and evaluate through the online leaderboard. People can also select to either show their results to public or just evaluate privately, such that people can the development loop can be private to the researchers. We also have 10 sequences, 2 for each challenge as training sets, where we release not only the data but also the control point data as post annotations for sparse control points, but also per keyframe pseudo ground truth poses, and hope that this can also enable some learning based methods that help scale the SLAM algorithm to large scale beyond the single rooms or single building. And we benefit from a custom recording profile, and this we were lucky to collaborate with Project Aria team, and in the end we only have data that are relevant to the dataset, so we don't have eye tracking data. Specifically, we have 2 SLAM cameras which are grayscaled global shutter and with 20 FPS, and also 2 IMU units with 1K and 800 Hertz respectively. On top of it, we have 1 RGB camera, which is unfortunately rolling shutter and 10 FPS. And because of the rolling shutter effect, modeling RGB can be quite challenging. So I think it is fair to say that at least for the initial development, the dataset is made for developing on top of the 2 SLAM cameras. However, maybe after the migrating to Aria Gen 2, there are more opportunities. And also in Aria Gen 2, the overlap is larger, so there can be more opportunities. We also have a GNSS receiver, and we also have Wi-Fi and Bluetooth. And all these modalities come from the Aria research kit. And compared to the LaMAria dataset, which only covers 3 isolated buildings, we include trajectories working from place A to place B, such that all these buildings are well connected. Here we show an example where we wear the Aria glasses and walk from the ETH campus to Lindenhof, which is a tourist site in Zurich. And all these recordings enable 40 to 50 minutes long recordings and more than 2 kilometers long trajectories in the dataset. And furthermore, as a key highlight of the dataset, we luckily benefit from the public control points from the city of Zurich, where they are maintained for construction purpose and actually actively measured and updated with the GNSS RTK stick. And this GNSS RTK stick is a surveying tool that provides longitude and latitude measurements up to 1 to 2 centimeter level accuracy. And some of the example control points are shown in the slides. So with that, we can georeference the trajectory with these control points and get unbiased post annotations. And this enables us to objectively evaluate SLAM methods with egocentric motion, regardless of the algorithm to construct the ground truth. The control points from the city provided data are actually with quite high density. In every 100 meters, we can find the control point. And this is a very good alternative to go and mirroring control points ourselves. And in practice, we also import all the city-provided control points into Google Map, such that before the recording, we go and find all these control points to be able to plan the trajectory capture and also geo-reference the control points with the trajectory. So the public control points are also mirrored with the GNSS RTK. And it works in the sense that it uses the GNSS plus some phase correction to a base station. And because it works in this mechanism, it has the limitation that it needs the line of sight to the satellites. So basically, it can only be measured outdoor. Well, in indoor, we need to resort to more subtle surveying instruments such as total stations, which is beyond the scope of this dataset. And this outdoor GNSS RTK stick has a nominal accuracy of 1.5 centimeter horizontally and around 5 centimeter vertically. So, and the vertical accuracy highly depends on the line of sight. These centimeter level accurate ground truths are more than enough to benchmark all the current existing SLAM algorithms running on top of kilometer level trajectories, where the top performing Aria SLAM system has a nominal accuracy of 50 centimeter per 1 kilometer. So this accuracy of the ground truths are far from saturated at the current state of SLAM research. So we also define some control points at the intersection of the roads and bridges to ensure coverage. And this set of custom control points we married ourselves. And in the end, it results in more than 450 control points in the city center of Zurich and spanning around every 100 meters. And each control points, to make sure that, because this is the sole source of our ground truths, we make sure that the control points are all measured correctly. Each control points are validated by 3 independent measurements on different days. And we found that from the statistical analysis, we found that the horizontal measurements is indeed accurate up to around 1 to 2 centimeter, and this aligns with the documentation of the GNSS RTK stick. To be able to geo-reference the measured control points, there are 2 solutions, and the first one is just to manually label every image, which is not accurate nor scalable. So here we benefit from fiducial markers, where we place the fiducial marker. Here is April tag on top of the control points we found through the Google Map. And then when we record the data, when we pass the control points, we place the April tag and we observe the April tag from different wheel points to ensure a stable triangulation. And then we can successfully georeference the trajectories with the measured control points. And here it is worth mentioning that the detected April tags are blurred right after detection as an additional step to the privacy-oriented blurring with equal blur. And this is because we don't want to have the tags shown in the release data, although some of them are still some of the detection are still missing, so we still have some missing tags that are shown, but we blurred a majority of the tags from the recordings. And this can prevent the SLAM algorithms to use these tags to actually use these tags as a feature to better track the key points and get behaviors that are not normal to in the real world cases. And here shows an example. We found a control point and we place a tag on top of the control points and we view it in different angles. And with all these viewing images, we successfully triangulate the control points and use these to georeference the whole trajectory easily. And we can also inversely use the control points to evaluate the trajectories, as I'm going to talk about here. So all these sparse control points can already readily evaluate any trajectory, and this benefits from a rigid alignment of the trajectory to all these control points. And specifically, for a given trajectory, say come from OpenWinds or OrbSLAM3, we estimate a similarity transformation from the triangulated control points from the trajectory to the ground truth control points. And in this way, we align the control point triangulation with the control point measurements, and we can measure the error between the estimation and the measurements, and then this control point error can serve as the evaluation metric to evaluate the SLAM algorithm. And all this evaluation work in LV95, which is a Swiss ENU coordinate system. So ENU is short for east, north, and up. So because in longitude and latitude is in the Earth coordinate, you need to convert it to the ENU coordinate. And this evaluation, as I mentioned, is agnostic to any bias from visual inertial optimization or other backend optimization algorithm, because it's solely from the surveying instruments. So it's reliable and unbiased, and it serves as our metric of the data set. We also additionally provide dense per keyframe annotation. So we get per keyframe poses as pseudo ground truths from a custom developed visual inertial bundle adjustment. So specifically, we first initialize our trajectory from the SLAM output of Aria MPS. And on top of it, we do keyframing and key point detection and matching following the SFM practice, and triangulate some 3D key points to be able to do the visual bundle adjustment. And here it is worth noting that this process is done with a light plus light glue rather than superpoint plus super glue. So both light and light glue have a good permissive license, so we can directly release all the data without any licensing issue. And we also pre-integrate the inertial measurements to relative pose constraints, and in the joint optimization, we do the visual bundle adjustment and also measure the inertial errors such that we can do a large-scale visual inertial bundle adjustment on top of the Aria MPS. But of course, our custom visual inertial bundle adjustment cannot be as perfect as the Aria MPS, but it serves as a good purpose, such that we can include the control point measurements as positional priors for this specific triangulation of the control points. And all these control points positional priors can reduce the drift from the Aria MPS and give a better trajectory shape with a good smaller global drift, because each segment is anchored with the control point measurements. But because we initialize with Aria MPS, it is worth noting that our dense per keyframe annotation is not available when Aria MPS is not reliable. So for example, on some of the moving platform sequences, the Aria MPS does not give a reliable result from visual inspection, then we cannot provide a good per keyframe annotation. That's also the reason why when we do the per keyframe recall, we don't include the MPS, because our pseudo ground truth construction is highly biased with the initialization from the Aria MPS. We did some covariance analysis on top of the visual inertial bundle adjustment problem, and we observed that the per keyframe annotation has an accuracy of around the 15 centimeter, which is not as good as the control points, but suffice to be good enough for kilometer level trajectories because the current SLAM algorithms are far from that accuracy. On top of it, relevant implementations of sparse alignment and multi-camera support from this LaMAria project are also merged as part of the COMAP developments in the COMAP 3.12 release in the end of June. This is, we hope to enable an experimental support of visual inertial optimization in COMAP such that more and more people from SFM or general visual localization community can think of this as an important problem because it's highly practical and there are more efforts towards this direction. And speaking of the new COMAP 3.12 release happening early this year, in this new release, we also supported arbitrary sensor rig that is not limited to the Aria camera, but also stereo or any arbitrary multi-camera device, and also panorama SFM, where you can render virtual images and consider it as a rig. But relevant to this data set, as we already discussed, however, we don't support time varying calibration yet, and we think it's beyond the scope of this 3.12 release, and we also don't support synchronization. But this is already quite significant add-on on top of COMAP, which originally only supports single images. And with all the prototyping happening in the COMAP format, we can actually compare two SFM visualization of the LaMAria dataset from 3 years ago and the SFM point cloud of LaMAria dataset. And on the left, it shows a building of ETH from the LaMAria dataset, while on the right, it shows a whole city center available from the 70 hours recordings of egocentric data. So this shows a significant improvement in terms of scale of the dataset, and I think this also proves that this dataset is quite a new iteration on top of the previous one. So let's do some recap. So we collected this list of SLAM datasets in the LaMAria paper to compare with LaMAria, where we capture kilometer-long trajectories with Aria Gen 1 classes. And we found that existing datasets used by classical SLAM research often overlook the specific characteristics of egocentric data from modern wearable devices, and they mainly rely on curated datasets for development, featuring very controlled viewpoints and restricted motion patterns. However, our newly introduced datasets includes multimodal data spanning kilometer-long trajectories with centimeter-accurate pulse annotations, and involves typical SLAM challenges. So, of course, the application of the dataset with such a scale is not limited to SLAM. So we also want to show some of the potentially interesting application of the dataset. And here, as David actually already covered, is an example of the photoreal project of Project Aria. And this is a task of novel synthesis, which is quite hot nowadays in the field of computer vision. And actually, when we collect the data, we know that the RGB data is rolling shutter. So we think it is a real problem, so we shouldn't include the novel synthesis task into the scope of the dataset. But with these new developments, where one can actually do novel synthesis on top of the rolling shutter RGB cameras. I think this dataset can also has potential to help at least prototype some novel synthesis on top of the RGB sensor of the Aria recordings. And another direction, because the dataset has such a large scale, it's natural that we can use these datasets to benchmark large-scale visual inertial bundle adjustment as a post-processing step. So in Aria MPS, I think the term is visual inertial VIBA as a post-processing. And here shows an example that is kind of relevant. It's also from Meta, developed called DABA. And this is decentralized distributed large-scale bundle adjustment pipeline that was released as an archive paper 3 years ago. And we hope that with a more centralized open source community, this kind of large-scale visual inertial bundle adjustment development can become easier. And last but not least, large-scale training is also another relevant, interesting direction that can be enabled with large-scale data. So now I know that there are a lot of heated interest in 3D visual foundation models, nominally enabled by Duster Master VGT. But in real-world scenarios, there are still a lot of open questions to be answered for these models. First of all these models only work on small-scale things. So it's interesting to see how they can maintain scale consistency over millions of frames. And secondly, it's unclear how they can efficiently inference jointly over multiple sequences or incorporate sensors like IMU in the end-to-end models. And there's also a lot of symmetry indoors when it comes to large-scale data. And because our ground truth is orders of magnitude more accurate than the previous data sets, we can give plenty of extra sequences for supervised learning as well. In the end, I want to conclude that the data set is, we have a live leaderboard, and I think Anusha will talk about details of this leaderboard in the next hour, but here shows some example where, again, open source systems are far behind industry solutions. Here, Aria Slam is far better than all the classic popular open source Slam systems. Finally, this is a joint effort between CVG group of ETH Zurich and Project Aria. And I want to mention that this is also a poster. Actually, we get highlights in this conference, and we'll present our poster in session 6 on Thursday. And we are excited to meet you at our poster. And that concludes my presentation. Thank you a lot. And next hour, Anusha will present more in-depth details of the benchmarking results of the dataset. And before that, I think we'll have another 15 minutes break, and we'll see each other at 3:34 p.m. Thank you.
Hello, everyone. I'm going to be continuing from these series of great talks and completing with our evaluation results. And I'll quickly start with a recap of everything that was covered regarding the introduction to the dataset. So as mentioned earlier, we have a pretty large set of sequences, 86 to be precise, and they're split into two, let's say, sequence sets. The first one being this controlled experimental set, and the second being the main data set. And in this data set, we have two forms of ground truth. I'm going to recap this. This was already covered by Shaohui. But to quickly recap, the first form of ground truth, which forms our high accuracy ground truth is our sparse control points. These control points are 3D points which are used in surveying and photogrammetry, and they were measured using an RTK GNSS rover. And these control points are, like I mentioned, our high accuracy points, and their measurement uncertainty is anywhere between is approximately 1.5 centimeters in the XY and 3 centimeters in the Z, so slightly more inaccurate in the Z, in the height measurement. The second type of ground truth that we provide is our per keyframe poses. These are obtained from our joint multi-sensor optimization, which was described in the previous 1 hour. And just to briefly recap how this was done, it's done by propagating constraints of the control points as position priors into the bundle adjustment, which also has visual inertial costs. The outline for today's discussion, for this hour's discussion, is I'm going to first start off by talking about our evaluation procedure, then briefly describe our systems of interest, an analysis on why we think existing data sets are not perfect, our main results on our main data set, and a case study on a particular challenge which was quite interesting. To start off with our evaluation procedure, I'll first start off with our high accuracy control points. So with these control points, we have a citywide network of 2D and 3D survey grade points. And like I mentioned, these are centimeter accurate, and they're also quite dense. They're located every 35 meters, as you can also see about approximately in the map. The way we use them is we perform alignment of each sequence estimated trajectory to its observed control points. And to talk about this evaluation, the main question that we want to solve is, given a rigid trajectory, how can we evaluate it against its observed control points? To do so, what we do is we have sequences which observe n control points throughout its trajectory. What we first do is we triangulate each control point from its detections in images. And this is done by minimizing reprojection error. So consider a sequence that has n control points. For n of these control points, we use the 2D detections from the April tag fiducial markers. And we triangulate the 3D position of the control point by minimizing the reprojection error of these detections. So now we have these triangulated control points from these detections on the Aria images. And we also have the actual measured control points which were obtained from the GNSS RTK stick. And how we perform this alignment is we find the optimal transformation that aligns these triangulated control points to the corresponding measured control points. So we finally obtain a similarity transform that we can use in our evaluation. To provide an illustrative example, what we have is, for example, a trajectory in its local coordinate frame. We have a set of control points which are observed in this sequence, which are in the Swiss reference frame. And then what we do is, with this optimal alignment, we basically georeference the trajectory to this LV95 LNO2 Swiss frame, which is an ENU frame which was described by Shaohui in the previous hour. And how we use this in our evaluation is the most interesting part, because this builds the foundation of our score and how we can determine what trajectory is accurate in and what isn't. How this is done is we have these triangulated control points which are aligned to the measured control points, and based on the error that is defined between these two 3D points, we can form a per control point residual error. And this per control point residual error is what forms the, is what builds the evaluation using these control points. And how this works is we have, let's say, a sequence with 5 control points, and you have 5 error vectors. And using these 5 error vectors, what we can do is we can then assign a score based on the error vector itself. So let's say if a control point has a very small error, it gets a higher score as per this piecewise linear function which we developed for our scoring. And an overall trajectory score is obtained as per the average of all the per control point scores. Now, some other ways which we can use this similarity transform in our evaluation is, the first is that we can also analyze scale drift of each trajectory. How this is done is we extract the scale from this optimized transformation, and then we calculate the error from the ideal scale value, which is 1. So if a trajectory is estimated very accurately, it will have, if it's estimated perfectly in terms of scale, then it will have a scale value of 1 from this optimal similarity transform which we obtain. The second type of additional evaluation that we can also do from this transformation is we can extract the rotation and then calculate the error with respect to, in degrees with respect to the world vertical. So how this works is we can get a gravity error, which is basically the angular deviation from the rotation in this optimized transformation, and the ideal vertical direction. And we have some results on Aria slam and its scale drift and also its gravity error, which will come a little ahead in the benchmarking. So this evaluation is our primary evaluation in this data set, since it's also our high accuracy evaluation. And some usefulness of this evaluation is that, like I mentioned, it's high accuracy. Second is that it also works on partial and failing trajectories. So for example, if you have a sequence that is not estimated fully, then those particular scores will be 0 for those control points. In this sparse alignment, what we can also do is we can add the 3D we can add the covariances of these 3D points in the alignment problem as well. So if, let's say, we don't have a Z measurement for a control point, we can set a very high covariance to that Z in this alignment problem. And like I mentioned, we also have some additional evaluations which we can run based on scale drift as well as gravity error. However, some limitations of this sparse evaluation is that it only evaluates the part of the trajectory where these control points are seen, and it's also useful only for global trajectory estimation. So if you want to, let's say, have some fine-grained analysis, this evaluation is not particularly useful. Another very important experiment which we also include in the paper, which I would also like to discuss now, is how reliable is this sparse alignment. So the main question that we pose is, let's say, since we're triangulating these control points from the trajectories that are estimated, are these triangulated control points themselves accurate enough, or does the uncertainty in the control point triangulation corrupt the sparse evaluation? And to check this and to validate our sparse alignment, how we do this is we consider the best available trajectory estimate of each sequence. In this case, as we discuss, I will discuss this in the later sections, but this is Aria slam. And I think based on the leaderboard images from all the previous talks, it was, we worked with Aria slam in checking the reliability of our sparse alignment. So consider this trajectory, which is a 12 control point sequence. What we do is we triangulate the control points from this estimated MPS trajectory. And then what we do is we iteratively run sparse alignment by leaving out a control point in each run. So in the first run, what happens is we leave control point 0 out, and then we run the alignment. In the second run, control point 1, etc., all the way till control point 11. And what we do with this aligned trajectory is then we predict the position of the left out control point of each iteration, and we define an error, which is the difference between the estimated triangulated control point as well from the measured control point, which is the RTK GNSS point. And the goal over here is to use leave one out cross validation. So it's just LOCV, in which we iteratively ignore one control point in the alignment process and then compare its alignment error with the aggregated uncertainty. And what I mean by aggregated uncertainty is just the combined uncertainty of the measurement, which is the control point measurement, and the control point triangulation. And some brief explanation about this triangulation covariance. How we get it is by the inverse of the Gauss-Newton Hessian from the control point triangulation problem. And this then can be converted into metric value by using the scale and the rotation from the optimized SIM3 transformation, which we get. So the aggregated uncertainty is the aggregated covariance is just the addition of this measurement covariance and the control point, the metric triangulation covariance. And what we do over here is we basically compare the residual error to these uncertainties. And as you can see, the control point error this is in log scale. So as you can see, the control point error is on average 70 times larger than the total uncertainty, which basically just suggests that our GT is sufficiently accurate and is not, the uncertainty in the control point triangulation does not corrupt this sparse evaluation. So this again supports our sparse evaluation, and like I mentioned earlier, this is our main evaluation, which also main unbiased evaluation, which can be used for any baseline that any SLAM baseline, for example, that estimates a trajectory. Then our second type of evaluation is the dense evaluation, which is over here, as Shaohui discussed in the previous hour, it's a per keyframe poses, which we get from this joint multi-sensor optimization, where we have visual inertial costs as well as control point constraints. How we run this is we initialize this problem with the Aria MPS solution. So as discussed in the last hour, if Aria MPS fails, then we don't provide PGT for per keyframe ground truth for those trajectories. But this optimization is basically initialized with the sparsely aligned MPS trajectory. So we have the MPS trajectory, we align it to its observed control points, and that serves as the initialization for this optimization. And how we use this in the evaluation is that we have a recall score at 5 meters, and this can obviously be more at different levels. But we select a recall score for 5 meters and we calculate this per keyframe error between the estimated trajectory and the pseudo ground truth. Some usefulness and positives about this evaluation is that it's fine-grained, so you can actually check errors not just at control point, not only at images that observe control points, but also the rest of the trajectory. It's good for measuring local drift, and this recall also works for partial and failing trajectories. However, it's not as accurate as our control points, and it's also not available for challenges, especially the moving platform, because in some cases we don't have an initialization for this optimization. Now, this concludes this introduction to our evaluation and our metrics, and then I'm now going to explain the input modalities that we primarily focus on. So in our benchmark, we selected monocular baselines, mono-inertial baselines, and multi-camera inertial baselines. And you might be wondering why we don't select stereo over here. Reason being that there is a lack of image overlap in Gen 1 SLAM cameras, which is why we don't benchmark stereo methods. This, however, is different for the Gen 2 cameras, but all our Aria Gen 2, but all our sequences are recorded with Gen 1, so we decided not to it doesn't make sense to benchmark stereo methods, but this can, of course, change with Gen 2. And then to have fairness in input, as this was already covered quite extensively in David's talk, this Aria camera model is particularly complex and is not supported in these open source baselines like OpenVins and OBSLAM3. And to support our evaluations, what we do is we undistort all the images to the pinhole camera and then input these images into various open source baselines. So this can be a little bit of a disadvantage because it reduces field of view, but I guess this was just a design choice which we selected. And then finally, we fed in factory calibrated parameters, which are per sequence, and these are fed in as configuration values to all the open source academic baselines. So this covers our setup of our evaluation, and now I'll briefly cover the systems of interest and which open source baselines we decided to evaluate. First, to recap about how we benchmark, like I mentioned earlier and also was in the previous hour, we have two sets. First being the controlled experimental set and the main data set. This controlled experimental set was set up so that we can figure out where these baselines are functioning, or if, let's say, our setup was incorrect of the baseline, and it was kind of our debugging set of sequences. We run as many baselines as possible on this controlled experimental set because it follows similar motion patterns that exist in existing SLAM datasets. And we realized that if a baseline fails catastrophically on this controlled experimental set, there's high probability that it won't work on the main data set. It just won't, it'll fail probably worse. So this is why we ran as many baselines as possible on this set, and then those baselines that succeed then move on to the main data set evaluation. What do we benchmark? Open source methods, we have a bunch of baselines ranging from filtering methods to optimization methods to direct methods as well as deep learning. And then we also, of course, evaluate the Aria MPS. Now, to briefly recap some of the systems of interest, I've tried to summarize each system as briefly as possible. OpenVins being the first one. So this is a filtering-based method. And one interesting thing about OpenVins is that it actually offers online calibration of camera intrinsics, extrinsics, as well as camera IMU time offset. And it supports monocular stereo and binocular plus the IMU. So we ran OpenVins on multiple configurations, and I'll get to this in the results section. It's a filtering-based method, so it's segregated separately. Then we have the optimization-based methods, which are OBSLAM3, OQUIS, and Chimera. OBSLAM3 it has both local and global bundle adjustment in its pipeline, and it's sliding window based. Its features are the OB, it utilizes features which are the OB features, and it also incorporates loop closure and place detection as well as global refinement. However, global refinement, I think for global VIBA, it runs only when the final map is, like the final set of keyframes is small enough. Otherwise, it just runs PGO. Over here, it supports mono and stereo, but like I described, we don't benchmark on stereo. So we primarily used OBSLAM3 for its monocular and mono inertial setup. Next is OQUIS2. OQUIS2 is an extension of OQUIS, and it's also an optimization-based visual inertial SLAM system. It's also feature-based. It actually supports final VIBA as well, although this extends the runtime quite significantly. And it optionally allows for loop closures. And in this case, we run it only in the binocular IMU setup for our benchmark. And finally, we have Chimera VIO in the set of optimization-based methods. Over here, it also optionally supports loop closure. And it's actually Chimera VIO is a part of a larger metric semantic SLAM pipeline. But over here, we benchmark only the visual inertial odometry pipeline. And over here, again, monocular and stereo, but we use it only in the monocular inertial setup. Then moving on to the direct methods, we benchmark DSO. And this is a direct method, and it only is monocular, so we cannot run it with the IMU. And it has no loop closure or no global refinement. And its extension is DMVIO, which integrates the IMU in its optimization as well. And it's the second direct method that we benchmark. Then moving on to the deep learning methods. First being DPVO. Over here, it also offers only monocular setup, and it also doesn't provide loop closure or global refinement, but its extension, which is DPV SLAM, which we also add in our benchmarking, is it includes loop closures as well as global bundle adjustment. But it has a SLAM backend and is built upon DPVO. So these are the learning, like the set of systems that we benchmark in the open source category. Apart from that, Aria SLAM, I've kept it very brief since we had a great first hour discussing Aria SLAM in detail. And over here, some important things about the evaluation is that we don't evaluate Aria SLAM on the controlled experimental set. This is because our pseudo ground truth is directly the MPS solution. And secondly, since we initialize our optimization pipeline with Aria MPS, we also don't evaluate in the recall scores, and we only evaluate Aria SLAM sparsely. This is also to keep the evaluation as unbiased as possible. So this was our setup of the systems of interest, open source and closed source. And now I'm going to move on to the first set of analysis, which is why our existing data set's not perfect. This is a recap on the results on the controlled experimental set. And the reason why we set this controlled experimental setup, some backstory, it was actually an afterthought to collect this data because we had collected our main data set sequences, and then we realized, okay, this is too challenging. Have we set up something incorrectly in our open source baselines, or is egocentric data just too difficult? So this served as our, let's say, debugging set of sequences to first understand why egocentric data is challenging, to then see the patterns of like system failure, especially in these open source systems, and then to also offer a reproducible set of just configuration tuning and also just sanity checks about whether we've actually set up our open source baselines correctly. So this is also a short set of sequences, so with different levels of difficulty, which I'll get into now. So starting with level 1, this was also discussed in the previous hour, but this sets up the stage for the evaluation results. As you can see, this is platform-based, it's not egocentric, and it's very controlled motion. The video, however, is sped up. This is not the actual speed. But it's controlled motion, and we only have in-plane rotations in this set of sequences. What we try to do is we try to emulate UROC. And in these set of sequences, we can see that our, like for example, the errors that some baselines produce are quite low, and which you can also see in the results of, let's say, when these baselines run on UROC. And like I mentioned, we have binocular, so multi-camera inertial, mono-inertial, as well as monocular. But as you can see, the errors are particularly low in this set of sequences. And our main takeaway over here was that these baselines overall just showcase extremely strong performance in these level 1 sequences. We've cherry-picked some examples here. There are the baselines which I described in the systems of interest. All of them have numbers in our paper, so anyone who's interested can check those as well. Then level 2, what we do is we try to amp up the difficulty a little bit more. It's still platform-based, it's still controlled motions, but we also incorporate out-of-plane rotations over here. And this is, like I said, just a little trickier than level 1, again, to have some granularity in understanding where, let's say, these baselines fail. And over here, our errors also showcase this. So in the previous case, it was 0.02, and over here, the error has increased in OQUIS. Similarly, for the other baseline examples, as you can see, OBSLAM 3 as well as DPVO they increase in their errors. And we can see over here that in-plane and out-of-plane rotations introduce these larger errors in these baselines. Then moving on to level 3, what we do is we incorporate more fast and complex motion. As you can see in the video, we have additional rotations. It's a little bit faster and less controlled, but still platform-based, so it's not egocentric yet. And this initial controlled motion is primarily so that we can help with the IMU initialization of these baselines as well. And over here, again, the errors get larger. And as you can see that, yeah, it's gradually increasing from level 1 to level 2 to level 3. And our takeaway, again, is as we kind of incorporate motions that get closer and closer to egocentric data, it just gets more challenging. And finally, level 4 is our, let's say, bridge between the platform recordings to our main data set, where it's egocentric, so it's head-worn. But what we do is we have this initial controlled motion, which is, again, just to allow IMU initialization for these baselines. And in this case, again, the errors are larger than level 3. And this level also showcases failures, complete failures in some methods as well. And our takeaway is that egocentric motion, it leads to either poor performance or just failure in these baselines. And those baselines that fail, we decided that if they fail on these set of sequences, then trying to benchmark them on the main data set is going to be more, it's just going to be just difficult to get results. So this is why we set up this controlled experimental set, so that we can understand where these baselines fail and what kind of systems would potentially be capable for running on our main data set. So to recap quickly, the different levels of difficulty in motion in this set, it's quite useful to showcase where SLAM systems are error prone or break. So for anyone who wants to use the data set, it's also a great set to start off with to see where, let's say, your system is facing issues. And another takeaway which we have from this set is that introducing this artificial initial motion actually helps with IMU, inertial methods for IMU initialization. But this is actually absent in natural egocentric recordings, because in natural egocentric recordings, the glasses are worn and you just start walking. You don't have this artificial motion. So this was another takeaway which we had from this controlled experimental set. Then moving on to the main results, which is the main data set. Over here, we have the 5 challenges which were described in the previous hour. To quickly recap, we have a short set of sequences, medium and long spanning all the way from ETH to central Zurich area. And we also have 2 other challenges, which are the low light and the moving platform. So our results at a glance. Over here, what you can see on the plot is basically the table where we have the Aria MPS score compared to the next best open source method for each challenge. As you can see, Aria MPS is just far ahead of these current academic solutions, and it's quite strong and performs very well. But our second takeaway from this set of study, from this data set, is that our Aria MPS is still actually far from saturating this data set. And this is because, as you can see, we set an error threshold of 1 meter to calculate this control point recall. And as we make this error threshold stronger and stronger, you can see that the recall values are extremely low, and in some cases 0 as well. So we believe this data set can help with just future iterations of Aria MPS as well, which is great. So, and then just one takeaway as well is that the nominal drift of MPS is approximately 50 centimeters per 1 kilometer in this main data set of sequences. Then another takeaway which we had was that this so we have OpenVINS, which is an odometry method. And what we did is we ran MATLAB, which is this backend optimization. And we can see that it improves the estimate of MPS when we run this, when we run MATLAB on the estimated OpenVINS trajectory. And this also kind of supports this full VIBA full final VIBA at the end of, let's say, these SLAM methods. And as you can see that the scores improve. And also from David's talk, when it was not included, you could see the scores reduce in Aria as well. Then another interesting thing that we studied was also the question that I would like to raise is just considering our longest sequence, which is 48 minutes and almost 3 kilometers, what makes this a challenging sequence to estimate? So it could either be just that the trajectory is just so large and it doesn't have loop closures, it's continuous straight walking from ETH to central Zurich, or it could also be this drift in extrinsics and camera intrinsics, which was discussed in the past couple of hours, that online calibrating this, the sensors is quite crucial for this large scale egocentric recordings where you can have bending in the glasses, some kind of changes in sensor calibrations, time varying calibrations, etc. So what we did is we performed some experiments using the estimated MPS online calibration file to check this. One thing to note is that this is, of course, not the ground truth calibration, but this is the calibration output of a system that is just very high performing. So what we observed is that over here in these two plots, left being the left camera and right being the right camera, as you can see, this is the change across time, across 48 minutes of the focal length when compared to its factory value. And these slight changes in camera intrinsics are noticed over this long duration of recording in the online calibration output of MPS. Similarly, if we also check the change in the rig extrinsic, in this case in degrees, you can see that there are slight changes in the rig extrinsic. So this is also being calibrated online and optimized in the MPS solution. And these changes kind of point out the importance of online calibration in just setting up online calibration in SLAM systems. And this is just another plot of rig extrinsic changes in centimeters over the long duration of recording. So we did this on just the longest sequence where it's almost 50 minutes, and you can see that MPS also performs calibration on in this case the rig extrinsics and the camera intrinsics. One interesting takeaway that we also had with this is that when we compare the OpenWin score with let's say if we don't have online calibration of intrinsics versus if we do, we can see a slight score improvement. Over here, the 3 bar plots are different runs because we also do multiple runs because there is observed variability in these baseline outputs. So to make sure that our evaluation is more robust, we have multiple runs as well. And across all 3 runs, the score improves. Then moving on to another takeaway is just how the results are when we have, let's say, mono-inertial or multi-camera inertial. And I think the direct conclusion over here is that adding a second camera just consistently boosts performance because you have more features, and yeah, you can see that that monocular is worse than binocular inertia. Then going back to the scale and gravity analysis, which we can do from the sparse alignment, from the sparse evaluation that we get out of the optimized Sim3D that we get from the sparse evaluation, you can see that MPS over here, it's on this side of the screen, you can see that MPS suffers from negative scale drift, and in the case of gravity error, it showcases almost a near upright alignment across all the challenges. This was our setup on the. This was our takeaways on the main data set. finally, to recap some possible directions which we believe are important also from the experiments that we performed. The first one being this online optimization of calibration of sensors, and also having this final visual inertial bundle adjustment, which boosts scores. So this is possible SLAM research, which we hope that our data set also helps with in the future. And then another takeaway is that we also tried to perform some short experiments where we tried to run methods like CoalMap and GlowMap on our full sequence set, but they simply just don't scale. They don't scale well to our full sequence set, where on average we have 33,000 images. And we hope that with this data set, we can kind of push the boundaries of large-scale evaluation and not just tests on short sequences like UROC, on like that some of the sequences that are in UROC and in TUM-VI, for example. So with this data set, we kind of hope that we can redefine the scale of evaluations, especially at this city scale at which we collect data. So this concludes the evaluation section of both the controlled experimental set as well as our main data set. And I'll move on to now a case study, which was a challenge which we found like particularly difficult for all baselines, including Aria SLAM, and is a specific challenge in our sequence set itself. One thing is, why is this a challenging problem? This was discussed in Marc's introduction as well as with Shaohui as well. So over here, as you can see, the visual features are compromised because you're in a moving platform, which visually looks like it's still, but it's actually moving. And the problem that's also difficult is this platform versus human motion disambiguation. So these two things are what kind of make it a challenging problem. And baselines in this category, as you can see, they perform quite poorly. The academic baselines especially perform quite poorly, while Aria SLAM leads the scores. But we also have sequences where Aria SLAM also fails in moving platform, some of our moving platform collected sequences. And this, for example, are some sequences where we unfortunately couldn't provide pseudo per keyframe ground truth because we just didn't have a complete initialization. As you can see, some two examples, one of them being it's incorrectly estimated over here. And in the other example, you can see we obtained a segmented output exactly in the tram path of the sequence. So there is a tram line that connects somewhere near ETH to central Zurich. So in this case, Aria SLAM also faces some failures in our moving platform sequences. And some small experiments that we ran to just see if we can try to improve our moving platform optimization is, since the visual constraints are not changing, what we tried is we tried to run inertial only optimization. And since the visual constraints can potentially mislead the motion estimation, we run inertial only optimization, and over here, as you can see, it's just not accurate enough and it suffers from a local flickering on the right. So it's just simply not accurate to run inertial only on these sequences. That recaps the case study of the moving platform, and now I'll briefly say what we plan to do with our data set moving forward. So the main thing being, we would love to, we are working on extending this work indoors. And since in Zurich, we don't have indoor control points defined, what we do is we perform indoor surveying. And how this is done is we have these outdoor control points which are defined by the city of Zurich. And we propagate these outdoor measurements into indoors at custom control points that we define indoors using total stations. And the idea is to incorporate indoor SLAM challenges like elevators and also room transitions between rooms, and also try to model temporal changes. And one, let's say, downside of the LaMAria data, the outdoor data set, is we don't have 3D data. And what we plan to do is we plan to also incorporate Navis 3D data in this extension so that we have just more geometry ground truth to provide. And we plan to also incorporate these control points into the Navis scans for this extension to indoor as well. So this was the end of my presentation. We can have a short, like a Q&A, and then I'll switch to the slides, which will recap how you can use our website to run evaluations. But yeah. So this is a practical guide on how to use our website to either download data or just get your results on your evaluation. You can find the website of our dataset at lamaria.ethc.ch. And the website offers downloading data, an online leaderboard, as was discussed earlier, documentation on all our sequences, and also a portal where you can submit your results. The first thing being, how can you access our dataset? You can download individual sequences in this dataset section. We offer 63 test sequences and 23 training sequences. They can either be downloaded from the dataset section, or you can use a download script which we provide in our repository. And there you can specify whether you want to download test data, training data, and what kind of data you want to download. A recap on what kind of data we provide. The first one being the raw VRS files, which are anonymized using EgoBlur. These raw VRS files are just the direct output of the Aria glasses. We also provide calibration files per sequence, because these factory calibration per sequence are not consistent across all sequences. They change slightly. This can actually also be extracted directly from the VRS file if you use the Project Aria tools. Then on top of this raw data, we also provide our benchmarking data, which is the data that we ran all our benchmarking on. This is in two formats, the first one being the ASL folder format, which is the format in which the UROC dataset was released. And the second one being the ROS format, because a lot of SLAM systems run on ROS bags. So we have both these data formats which can be downloaded. And since we understood all the images to pinhole, we also provide the pinhole calibration files per sequence. And then, of course, for the training sequences, we have both the sparse and the dense ground truth provided. A quick recap on the formats of the ground truth. So the sparse ground truth, in this file, you can find control point name and the tag ID on which the April tag, like the associated tag ID that we used in the recording. You can also find the GNSS 3D measurement as well as the 3D uncertainty of the measurement that we obtained. And then you have all the detection information on which image has this control point detected, the timestamp, as well as which control point was detected on that image, as well as the detection in UV pixels. Our per keyframe pseudo ground truth is in the standard TUM format, which is quite commonly used. Over here we have timestamp, translation vector, and then the quaternion. These poses are defined in the left SLAM camera frame, and the timestamps are in nanoseconds to keep it consistent with the Project Aria timestamps from the VRS files. To evaluate via the website, you need to create an account. You can then submit results to either the training or the test sequences. Results on the test sequences will be published on the leaderboard. They can either be published with the actual submission name, or they can be kept anonymous. And then I'll recap the submission format. So this submission format should be in a zip file, which when unzipped, it breaks into this folder structure. Each estimated trajectory should be a TXT file with its name that you can find on our dataset section of the website. And the format of the submission is the same as the pseudo ground truth, where we have the timestamp, the translation vector, and then the quaternion. For inertial methods, we expect the world from IMU pose, and for monocular or binocular, we expect the world from cam0 pose, where cam0 is just the left SLAM camera of the Aria classes. To create a new submission is fairly straightforward. You log in and you will automatically be directed to a section where you can create a new submission. You can upload a zip file in the correct format. And as soon as you upload, depending on the number of sequences you submit, the evaluation will run and the results will be available. For example, once your evaluation is complete, you can find your results in a tabular format for that particular method, readily available when you click on view results. And as you can see, we also, if let's say you have a new SLAM system on which you would like to benchmark on our dataset, you can also provide additional details such as the website, the code, the programming languages used, some parameter settings, or you can stay completely anonymous as well. Training sequences are not published on the leaderboard. It's only the test sequences which are published. And as you can see over here, this is the current state of the leaderboard. Right now, we have provided some baselines, which is our results of our benchmarking. And this serves as an online live leaderboard. And we also have summary as a summary leaderboard, which is basically the average of all the scores, or let's say the recall values across all the sequences in that particular challenge. You can also select from the drop-down a particular challenge that you would like to view and the results of per sequences. One note is that your method will have a score on the summary leaderboard only if it has submissions for all the sequences of that challenge. If you would like to not submit a result for a particular sequence, you can just submit an empty TXT file and it'll automatically provide a score of 0 and recall of 0, for example. But to appear on the summary leaderboard, you should have submissions for all the sequences of that challenge. And then finally, we have two ways in which you can contact us for any questions regarding the dataset. We have the GitHub issues on our GitHub repository. You can raise questions there regarding either the code or the dataset itself. We also have a contact form on the website using which you can send us a message if you have issues with some data or issues with some evaluation, something that you think is going wrong. We'd love to hear from you and just any feedback in general. But that concludes my practical guide. And if you guys have any questions, just contact us in any way.